Good morning or good afternoon, everyone. Welcome to the last session of the week. We've had a fantastic week so far, so let's finish it off with our fourth session. So, Lawrence, over to you.
Right. Thank you. Uh, good morning, afternoon, evening, everybody. Thank you for joining. I hope you enjoyed your taste of Solidity yesterday. We're going to carry on really a mixture today. So we're going to talk a little bit about Solidity, but we're also going to talk a little bit about Ethereum as well as a little bit of theory. I want to just go through quickly the first couple of homeworks so we get those out of the way. And the first one, I mean, this was meant to be a discussion for you in your teams, and it was trying to look at the problems that you face if you're moving from a centralized uh, service or system to a decentralized one. And so I think a reasonable example for this is something like a game like Monopoly. And if you imagine you're playing this with some friends, um, but there's no central server, so you have to find some other means of communicating your moves, etc. And it brings up a lot of the problems that you find when you start to think about how blockchains work and how decentralized systems work. And so the the essential pieces of functionality are, the parts of the game of Monopoly. So things like keeping track of the money that people have and their position on a board. And this is problematic in that you have to then try to work out how you're going to replicate that. So presumably you would have some means of, maybe you would email each other the moves, or you would perhaps have some video to show people making moves or whatever. But what you're going to do eventually is to do really what similar things you have with blockchains and nodes, where you have a local copy of the state of the system. So maybe locally you have a board, and then you keep track on that where the other players are and how much money they have, etc. And the problems that you could get is you have to solve are things like how you keep track of the amount of money that people have. So how do you prevent people from just giving themselves more money? So you would need to have some system of doing that. You need to have some. You need to keep track locally of how much money each person has and how you would update that. Um, and similarly with the board positions as well. So you would have to have some means that these changes to the money they have and changes to the board positions would get transmitted to you, and you would be able to validate that these were correct. And so, for example, you would make sure that somebody has moved to the correct place on the board, or that people have the correct amount of money. So this is very similar to the idea of having transactions on a blockchain and then running those against your local copy of a ledger. The other thing you would need to think about as well, possibly, is the question of identity, and you may need to restrict the people who are joining the game, or because you would want a certain number and certain people in the game, so you may need to do some sort of permissioning there. And then also the idea of the identity of the people and the transactions that they do, you would want some means to know that they were correct when you receive them. So the fact that somebody hasn't sort of created some transaction, it hasn't been interfered with on its way to you, or the correct people are sending you the transactions, and the transactions that you see are from the correct people. So those are the ideas I wanted you to think about. And we shall see, the thinking about games is quite useful when we're thinking about decentralized system, because with centralized systems, they work reasonably easily. In a decentralized world, they don't. But having the idea of games and the game theory that's involved in those is very similar to the kind of game theory approaches you need to think about when you're looking at blockchains. Okay, so that was the first homework. And then the second one, again, it was for discussion, for you to think about the getting the incentives right, and the crypto economics of a blockchain. the first two parts, really, I think I'd given you those pretty much in the notes anyway. That if you have a blockchain system, there's some things you want, some behaviors you want it to have. So things like you probably would want it to be open unless it's a permissioned chain, so that anyone can join, and you would want it to have liveness, so you don't want the blockchain to stop at any point. You want it always to be able to continue, and so you should always have some means of recovering if there's any questions around consensus. You would need something around that. It should be, to incentivize the people to interact, you need to make sure it is not expensive or difficult for them to join and interact with your system. And then you need all of the things around cryptography that ensure that the transactions that people are doing are correctly signed, and from those, and are not able to be manipulated or forged in any way. And it should also, you think, want things like robustness as well. So these are the basic properties of blockchains. And these have been incentivized in Bitcoin via economic means. So the fact that doing the proof of work algorithm has an economic cost, that gives people an incentive not to be malicious and to do this correctly. And similarly with transactions, because you pay a transaction fee if you want to send a transaction, this disincentivizes people from spamming the network with spurious transactions. The second question about 51% attacks in proof of stake. So these are possible. Now, the thing to remember is the 51% attack is an attack on the Sybil part of the kind of the consensus mechanism, the whole thing. So if what you're doing with a 51% attack is to try to increase your chances of being chosen as a block producer. So it's not the consensus part that you're attacking. It's the block, the choice of block producer part that you're attacking. And so in proof of work, this involves your chances of being chosen are all down to the hash rate that you have. So in proof of stake, your chances of being chosen are typically down to the amount of currency that you own. So to do a 51% attack in proof of stake, you would have to control 51% of the currency that is being used as a stake. So still possible, but probably quite a little bit more difficult. Okay, so I hope you had some good discussions in your teams about those. We'll go through the other homeworks later. So let's. I want to go through a little bit about Solidity that we didn't cover yesterday. As I was going through the example on Remix, we didn't sort of get time to do everything, but it's in the notes from yesterday. So one thing I don't think I said, but it is in the notes, is the idea of getter functions, and the fact that you can declare a variable as public, and this will automatically create a getter function for you. So it will create a view function to get that variable for you. So that's a way to a sort of shortcut for you to get a function written for you without having to write it. So maybe instead of writing our get score function, we could have made our score variable public, and it would have created a function for us to retrieve the score function. Okay, and then we did events, so that's good. Now, we didn't cover some of the reference data types, so I'll go through these now. So we covered the simple data types such as uint, and address, but we didn't cover the reference data types, the more complex data types. And one of the ones you will find most useful is the mapping. And if you're familiar with other languages, then the sort of equivalent in those would be something like a dictionary or a hash map, something like that. And a mapping is it has key value pairs, so it associates a key with a value, and when you declare the mapping, you have to specify the key type and the value type, and then give the mapping a name in just as it has there. And there are restrictions on what you can use as the keys, and I think that they kind of make sense. You need something that is quite you need still simple types for the keys. And then if you want to retrieve the value associated with a particular key, you use square brackets around the key. So in this example here, we have the mapping. We're mapping between the address data type and uint, and then to get the uint for a particular address, we specify the mapping name, score list, and then the user in square brackets, and that will bring us back the value for that particular address. Now, one thing that you will find is annoying in Solidity is the fact that we cannot iterate through the keys within a mapping. And there are libraries that will help you with this. So there are libraries you can use to get around this. But one approach is that you could use is that when you add keys into a mapping, you also add those keys into an array. So you can iterate through an array. So you could have, for example, an array of addresses, and then and if you keep that in sync with your mapping, then you could iterate through your array. And as you pull out each address, you could then go to the mapping and then get back the value for that particular address. So that's one quirk of mappings in Solidity. That's a little bit annoying, but that's what it is. Reference. I'm not sure why it's called reference data type. That's just that's just what it's called. Well, for these things. Well, actually, it is. I think that's probably down to the way it is stored. Actually, so the reference data types, mappings, and arrays, and things that are dynamic in nature are stored in a different way to the simple data types, and effectively they have a reference to where they are stored. But that's something that we'll cover much later. Yeah, so I've covered the public idea. Arrays, so I just mentioned those. These are, you should be familiar with these. These are similar to the arrays that you have in other languages. So you just declare them. You can either have them as fixed size when you declare the size along with the declaration, or they can be dynamic. And yeah, you use them the same way that you use arrays in other languages, and they're zero indexed, and you use square brackets to get back the particular item in the array. So quite straightforward. And there's a couple of methods that you can use with them. So you can get the length, and you can push items onto the array, so you can yeah, get the item, put those onto the end of the array. And yeah, there are other things as well, but yeah, that's all we need for a moment. Now, if you want to combine some data types and sort of create something a little bit more complex that makes more sense to what your contract is doing, you can create structs. And again, I think you're probably familiar with these from other languages. So this is a way of creating your own sort of complex data type or composite data type. So you start off with a struct keyword and then give this some name, and then within the curly brackets you put the data types and a variable name for the items that make up this struct. So here we're saying that we have this object called funder, which has two parts. The first part is an address, and the second part is a uint. And then once you've declared it like that, then you can use it. You can create a variable of that type. So giver now is of type funder, and it will have two parts to it, an address and an amount. And to reference those parts, we use dot notation. So you can say giver.addr equals something, and giver.amount equals something. And that's how you reference the types within the particular struct. And yeah, we've got some examples here. There are different ways to, I'll just give you a couple of ways there of creating an object, sort of creating a struct and putting that into an array. So you can use this. The second one is perhaps familiar. It's got more like the sort of the JSON format, where you can specify the you use curly brackets and you specify the name of the element within the struct, and then you pass in the value. But either way is fine. Okay, so that's I think enough for you to be getting on with. In terms of the Solidity, we will come back to more Solidity details next week, so we'll go into more things next week. To answer the question, are structs allocated memory in the stack when the smart contract runs? No. So this, when you declare something, it's not actually, it doesn't it doesn't go into the stack, but we'll, right at the end of the course, we'll talk about the stack and how that works. So it's not actually, yeah, the memory and the stack are actually different anyway. So can you explain the use of underscore? So the two places perhaps where you've already seen underscore is, one of them is just part of a convention when you're writing a function and you have arguments to that function, and the names for those arguments. A convention is that you put an underscore in front of or you start the name with an underscore. And so that this is just to increase the namespace, so that when in your function, you don't then conflict with something that is similarly named in contract scope. And then the other time you see them is in a modifier where the underscore represents the place where the function goes within the modifier. So that's the other place. If you deploy a contract with a vulnerability, how do you fix that? We'll come on to that when we look at upgradability in contracts. So I'm going to move on to looking a little bit more at Ethereum in a little bit more detail. So we've done a review of last lesson. So we're going to talk about storage, accounts, and transactions, and a little bit about languages, clients and mining. We'll just mention briefly, and test networks as well. I've got some reading material there if you want to have a look at that. There's some very good articles and books. So DEFCON 1, I mean, that was quite a long time ago, but there's a talk there from Vitalik about Ethereum. Anything by Andreas Antonopoulos is good. So, but his book Mastering Ethereum is very good. It goes into a lot of detail. It's really nicely explained. And then the last three links there, there are to a number of papers. And if I start to the bottom, the yellow paper is the most rigorous and comprehensive. That is the standard really of how Ethereum works. And then the beige and white papers are the variants of the yellow paper, but they're perhaps a little bit more user-friendly. They're not so rigorous. They're easier to understand. So just to say about upgradable contracts. So we will cover those. We'll have a whole lesson about upgradable contracts later on. So I'm not going to cover them now. In fact, I mean, as a general point, I should say that there are a lot of things that we will cover later in the course. So I'm going to keep saying this, that, we'll start off with the basics and we'll cover other things later. So we'll do that later in the course. I'll explain all about that. So what I want you to think about at the moment is, and this is really sort of tests your understanding of how blockchains work, and Ethereum in particular, is to think about the state in Ethereum and where actually does it exist. So if you think about, if you imagine you've written a contract and deployed that onto mainnet, perhaps you've used the score contract. So in the score contract, there was a variable called score. So this had some state. And what you want to think about is where actually is that score variable held? Where would you find it if you wanted to sort of look at the hardware where it was being held? And also how, is that in blocks? Is that in a transaction? And who is storing this state? So these are the kind of things you have to get straight in your mind when you're thinking about Ethereum and thinking about things and thinking about the state of contracts and the state of Ethereum overall. And it's a little more complex than you might imagine. One of the data structures that Ethereum uses is a thing called the Merkle-Patricia tree. And this is a variant of the Merkle tree, but it's, and I won't go into all of the details of this because it does get a little bit complex, but it's used so that you can search in it quite quickly. And the items in this tree are laid out so that the data is at the leaf nodes, the important data, but the items are laid out so that these data items come in order, and the path to those data items is made by sort of looking at the actual bytes within the final data item and creating paths for those. So as you can see, if you start at the root and follow A and then 2 and C and 7, you get the data item A2C7. And that is there because that's sort of placed there. That's the path that you need to follow to get that data item. And that comes before the A2B6 data item, which is before the A62 data item, etc. So these things are, they're organized so that you have some ordering amongst the data items, amongst the leaf items, and these this makes for efficiency, but it is a little more complex. But I wanted to introduce this terminology because you will see this. Typically speaking, you don't, unless you're going into the blocks and the state in a lot of detail, you don't really need to think about this too much, but you will come across this this term. And then if we consider a particular a block, this holds a number of things called trees, or it's spelled TRIE. You can pronounce it try if you like, but I think it's basically called pronounced tree. And these are there to specify or to help validate the state of Ethereum. There are a number of these, and the main one is called the world state. And this is a mapping, so a key value mapping between addresses and account states. So for a particular address, you will get an account state, and that's the state that's on the left here. So this is the state then for a particular account. And so for a particular account, we're storing a nonce, a balance, a storage root. So this is the Merkle root for that account, and then a code hash. Now, so if I go through those in turn, the nonce is needed. And you may have come across this if you've been interacting with a blockchain and using a wallet. The nonce is there to keep track of the transactions that this account has done on the blockchain. And it is a way that you can ensure that transactions are not missed. So when you send a transaction to the Ethereum blockchain, it's the node that receives your transaction will be able to read the last nonce that you used, because it will have details of your account, and it will be able to compare that to the nonce that is in the transaction that you are sending. And it will assume, or it will expect, that that nonce has increased by 1. If it has increased by 3, it will assume that there are 2 other transactions somewhere that it hasn't seen yet. So it won't process your transaction until it finds those other 2. So it's a way of making sure that it doesn't miss transactions that a particular account has. And this can be problematic when you're creating transactions. If you're doing these transactions manually, you have to ensure that this nonce is always increasing by 1. And if you send a transaction that is the same, has the same nonce as a previous transaction, then the node will expect that to be a replacement transaction. So think that you're trying to replace the previous transaction with a new transaction. And if you do that, you have to pay more gas. It expects the gas to increase as well. So this, you don't need to, well, you'll come across this more when you're looking at Web3 and when you're looking at creating transactions, but it's something that does catch people out quite often. The second field, the balance for the account, is just what you expect. It's the amount of ether that account has, and it's measured in Wei. So this is the lowest denomination of ether. And then the storage root for a particular address is the root of the Merkle tree of any key value pair items that are associated with that address, because this account could be an externally owned account, so like a wallet account, or it could be a contract. And if it's a contract, then you have to store all of the variables for that contract as key value pairs, and they will be then in a Merkle tree, and you will get a root of that, which you will store against the account. And also, if it is a contract, then there will be a hash of the code of that contract. If it's not a contract, then these 2 fields will be effectively 0. But if it is a contract, then you'll expect to see a code hash and some storage associated with that contract. So that's that's held for each account, and then all of the accounts are bundled up into the world state. And then we also have transactions, so a tree of those, and these have each transaction has a number of fields. I'll go into these in more detail in a little moment. So I'll go through this. Just to have a look at some of the questions. Yeah, so again, MEV, we'll talk about that. We'll have a whole lesson about that. But typically speaking, the amount of transaction fee you're willing to pay will, if you pay a higher fee, that makes it more appealing to a miner, and they're more likely to include your transaction ahead of another transaction in a block. So, but I'll go into that a lot more detail later. And the nonce of a particular Ethereum address, yes, you can read this from a node. So when we look at interacting with accounts and contracts, we'll see how you can do that. But also, if you look in wallet like MetaMask, you can see that there's a way that you can see advanced details, and you can find that for your own address there. Okay, so transactions, yeah, we bundle them up into a tree in the same way as we do with accounts, and I'll go into the fields for a transaction in a moment. And then the final tree we have is what's called the transaction receipt, and this gives you details of the results of a transaction. So the transaction itself is the input, really, and then the receipt is what has happened from that transaction. And as part of that, we have these things, log entries, and we have something called a Bloom filter. And a question that people often have is, are events held on the blockchain? And the answer is slightly complex in that, no, they're not exactly, but we have this thing called a Bloom filter that gives us details or gives us a sort of a probabilistic detail about events. So what a Bloom filter is, a specially designed data structure. It's a probabilistic data structure that is space efficient, and it answers a question. You can ask it, is an item included in a particular set? And the Bloom filter will answer either it is definitely not in the set, or it may be in the set. So it can't tell you that it definitely is in the set, but it can tell you that it's either definitely not in the set or that it may be in the set. And we use this when we're looking at we're trying to get events from a block, but I can explain that a little bit later. If we look at a block in Ethereum, what does it contain? And so I spoke before about the separation of header and transaction areas. Generally, and in Ethereum, we also have a thing called the OMA block headers as well, which I'll go to in a second. But the header area, this area is there. This is all about validation. This is what you're looking. This is what you're using to validate that the blocks are chained together correctly, that they haven't been interfered with. So it contains the hash of its parent header. So that's straightforward. The OMA, I'll come on to in a moment what they are. The beneficiary, this is the person who receives the block reward. So it's often can be called Coinbase as well. And then the state root. So this is the root of the wealth state. The transaction root is the Merkle root of the transactions, and the receipt root is the Merkle root of the of the transaction receipts. And then we have the Bloom filter. So we have that in the header. We have the difficulty for proof of work. The block number, obviously that's going to increase. And then we have gas limit and gas used. So the gas limit, so this is going to be fixed typically for a block. So this can change, but this will require a change to the protocol. So typically for a number of blocks, the gas limit is the same. But then the gas used will vary in blocks. So the blocks may not be full in terms of gas. The timestamp is a rough guide to when this block was produced, but it may not be accurate. And remember that the miner produces this, so they can alter this to their advantage if they like. There is a field for extra data this is not validated. This is there for you to put in other data if you want to. But it's not part of it's not validated as part of the protocol. The mix hash is an item that is used for mining, and I'll explain a little bit about how mining works in Ethereum because the mixed hash is used with that. And then there's also the nonce, which is used for the proof of work. So to answer the question, so yeah, I said the limit is not, the gas limit is not constant. It can change in that it could change because of a hard fork or a change in the client software, but it is going to be, typically speaking, it will be the same for any number of blocks. And it is needed. You need to be able to check that value hasn't been exceeded. And yeah, I did say about the transactions. So the transaction root is the Merkle root of all of the transactions, and that is different from the Merkle root of the transaction receipt. So for a transaction, that is the input, and you have a transaction receipt. So they are different things, and so the roots between those are different also. Okay. Now coming on to these OMA blocks, or they're also called Encode blocks. And this is a way that Ethereum differs from Bitcoin, in that in Bitcoin, if you have an orphaned block, then the miner producing that block doesn't get a reward. But in Ethereum, they have decided to give people who produce orphan blocks a reward. It is a smaller reward, but it is a reward. So what this means is that block is not completely discarded. It forms part of the canonical chain, but the transactions within that block are not part of the chain. So when we have an OMA block, we get rid of the transactions in the OMA block, but we keep the header and we keep a reference to that. So when I spoke about the fields we have this hash of the OMAs, and we have block headers for those OMAs included in our current block. And the reason for this is that in Ethereum, we have a much shorter block time. So we're producing blocks more often. So orphaned blocks are much more likely. And we want to incentivize people to carry on producing blocks and not be put off by the fact that these blocks might be orphaned. And the fact that we have these blocks as part of our canonical chain also adds to the security of the chain, because it means work has been done to produce that block, and that is sort of set within the canonical chain as well. And so the security of the whole chain is increased by having these OMA blocks in there. And so they do get a reward, but it is smaller than the normal block reward. And yeah, we don't have transactions. The types of accounts in Ethereum, we have two. There is the normal account, the sort of the accounts you see in wallets. These are called externally owned accounts, and these are controlled by, well, probably people, or they could be some software, I guess, but it's certainly not controlled by contracts, and they have a private key and they can initiate transactions. And I want to contrast those with contract accounts, which are controlled by a smart contract itself, and those do not have a private key, so they cannot create a transaction. And that is also a restriction, I suppose, on what we can do with smart contracts, in that they can't create transactions. And the various methods have been suggested and projects built to try to get around this and try to produce this functionality of being able to create transactions automatically on Ethereum. So the account state, I've been through those, so I won't go through those items again. And then if we start to look at transactions, remember that a transaction or a set of transactions represents a state transition from a world state at a particular time to a world state at the next increment of time. And when the individual nodes will apply the transactions to the current world state to get to the next world state. The field that the transactions have are listed here. So one recent addition to the transaction is a transaction type. So there are legacy types, which is what you will see mostly. Most transactions are legacy transactions, but there is a new type which is specified in this improvement proposal 2718, which allows for transactions to specify, give more details of what this transaction is going to do in terms of the storage. So they're quite a specialist thing. They've been introduced to help with scalability, but yeah, typically we sort of at our level we don't sort of have to worry about those. Then the second field is the recipient, the address that is going to receive what this transaction is doing. So if your transaction is, for example, sending Ether, then that would be the address that is going to receive the Ether. If it is interacting with a contract, then that would be the address of the contract. We need a signature to make sure that we can identify the sender of a transaction, and this is created by the sender signing the transaction with private key. And there are methods that you can use to then recover the address of the person who has signed the transaction. So you can validate who that transaction has come from. The next field is a value field. This is the amount of ether that will be sent along with the transaction if you decide to do that. And you may remember yesterday when I was talking about Remix, I showed you the transaction field I showed you the value field within Remix, and that you could change that to send in some ether along with your transaction, and that is denominated in a way. You can add in data to your transaction if you like, just some arbitrary amount of data, and then you can specify a gas limit that you want your transaction to be constrained by, if you want to. Otherwise, it is going to be constrained by the gas limit of the block, or the amount of gas that you have been willing to pay for in terms of the figure that you have provided. And then in terms of the fee, this has recently, well, almost a year ago, the way the transactions fees worked has changed in Ethereum. And so we now have two fields that specify the figure that you're paying. So there is a base fee, which is paid, and then there is this an optional tip that you can pay to the miner on top of that. And so each of these you can vary the amount that you're willing to pay for those. And some important things to bear in mind: the miner will choose a transaction. They choose the transactions that they include in the block. And so this gives the miner a great deal of power. And when we look at MEV, we will look at the implications of this. But yes, you definitely need to remember this, that a miner can choose to drop as many transactions from the block as they like. They don't have to include any transactions. They can produce an empty block if they wish. And they can decide upon the order of transactions within the block. They can also create their own transactions and add those to the block, which means that they would be creating transactions that might not be seen in the mempool of other nodes. And typically, your transaction is in competition with others for inclusion in the block. And this is known as the gas priority auction. It's really the case that, in general, the higher the transaction fee you're willing to pay, the higher in the block, or the more likely to be included in a block will be your transaction. And then a note about processing transactions. So I want to sort of emphasize here that transactions are atomic, and this leads to some very interesting features about transactions that we'll come on to when we're looking at decentralized finance. But the point is that if you imagine you have a number of statements, a number of lines in a particular function in your contract, and you start your transaction and you're running through these lines, if your transaction completes without error, then it may introduce a change of state. So in this example, I've said that there will be a change of state in an account balance from 5 to 10, and once the transaction is completed, then that state will have changed. If, on the other hand, partway through this transaction, the virtual machine reverts the transaction, or alternatively, the code could decide to revert the transaction, then all of the state change that has happened will be reverted also. So the state at the end of this transaction will be the same as the state at the beginning of the transaction. So this is just really to emphasize that the transaction is atomic. Just an introduction to the virtual machine. So you can think of it as a distributed state machine. So it's moving between states. You have these state transitions, which are made of transactions, and it moves between these according to the predefined set of rules, the protocol that you can read in the yellow paper. And yeah, this really is just a diagram to show the thing that I said before, the fact that there is a transition and this is atomic. It is the design of the EVM is, well, some people don't think it's maybe not the best design, and it is perhaps not designed in the same way the way that a lot of virtual machines have been designed. In particular, we have this fact that the word size is 256 bits, and this is a great deal more than most virtual machines, and it was done to facilitate the cryptographic operations, but it is perhaps not the most optimal way of doing operations, because you're doing operations on 256-bit items at a time, which may be much larger than what you need. But anyway, that's the way that the machine is at the moment. And then when you're storing, when you have variables in that are being used in your contract, there are two sort of main areas that these will come from. One is the storage, which is the contract storage, which is persistent, and this remains the same throughout transaction calls. And then there's the memory area, which is wiped after a transaction completes. So anything in memory you will lose after the transaction is finished. So it's just a transient area that can be used by the contract while it is processing your transaction, but it is not kept. Just to answer questions, is there a time limit? I think I don't think there's a time limit enforced by the clients. It's more a case of the amount of gas that you use. So the limits you have on a transaction is denoted in terms of gas, which is really the number of computational steps that your transaction can have. And you have to bear in mind that transactions are meant to be quite small in nature, and to do a large number of steps will be prohibitively expensive. And if you run out of gas as your transaction is running, then the EVM will revert your transaction. And so for your transaction to take a long time, it would have to go through a large number of steps if you assume that the client is running efficiently. So in that sense, there wouldn't need to be a time limit, because the client will just apply the gas limit to your transaction and stop your transaction if it uses too much computation or does too many computational steps. If the client is not very efficient, then it will generally be slow doing transactions anyway, which will mean that it probably won't be able to keep up with the network and keep up with the processing all of the blocks, in which case it would eventually just drop off the network, and it would just be spending all of its time synchronizing rather than processing transactions. So those items that would sort of really define the time limit for transactions. Can we have a maximum of 5 items in the stack? No. I don't know why you think 5. Yeah, there are limits, and you may get an error, but unless you're interacting directly with the stack, you don't really have to think about that. The gas usage, you can pre-compute it in the sense that it can be simulated. It's what the contract does is deterministic. So before you run your contract, you can get an estimate of the amount of gas, but that could change if, for example, you're interacting with other contracts, and since you did your estimate, those contracts have changed, and so that might mean that your interaction requires more gas. So it is determined at runtime in the sense that that's where it matters, the amount of gas is used, and that's where the limits are applied. But you can get an estimate for that, and it's reasonably accurate. Time and space complexity, yes. So the advice I would give you when you're writing your contracts is to keep what they do, to limit what they do, because computation and space are very expensive. I mean, space in particular is very expensive. So, but I'm not sure what you mean about the logging. Oh, I see. Authentication. Well, yes, you need to be careful about the security. So there will be things that you need to do. So I suppose the general advice would be do the minimum amount that you have to do in your contract. But some of that minimum amount is going to be security, and that is very important. And for a reverted transaction, yes, you do get charged for the gas for that, to some extent anyway. Okay, so the question about the function being, the contract function and the transaction being mined successfully, it's a bit of you've got a misunderstanding maybe there, because transactions are submitted, and they will be validated by the nodes that receive them, and then will be passed on to other nodes. So they have to be valid to some extent. Then the miner will run those transactions and produce a block, and then that block will be passed around. But before that block is produced and passed around, the other nodes in the network will not know which transactions that they will want to include next. So it's the block that is specifying those. And then the other nodes in the network need to run those transactions because they need to update their state. So they need to update their local ledger. So that's why it is needed. It's not a waste of computation. They need to do that. Yeah, we'll talk about other blockchains later. I don't want to get into a big debate about the gas fees at the moment. We need to sort of go through the essentials now. So is the stack connected to the storage? So the stack is separate from the storage, and the stack is separate from memory. But we will go into that sort of in the last week of the course, where we look at doing assembly. It's not something you need to be aware of when you're writing your contracts now. When we do that, we'll look at opcodes. So these are the basic codes. If you look at the bytecode, you'll see these types of things, but they are just the types of codes that you would expect to see. You don't need to worry about those now. In terms of languages, there are a number of choices that you have. The most popular one is Solidity, so that's good news for us. But other ones have been around for a while. There is one LLL that has been around forever, but I don't know if it's still maintained. It's low level and it's like Lisp. The sort of competitor to Solidity, I guess, is Viper, which is similar to Python in syntax. One that we will look at is Yaw and Yaw Plus, which is an intermediate language, so it's going towards assembler, but it's a little easier to use. And then a more recent one is FE, which is still being developed. So this is a very recent language. And then other ones, these other ones I've mentioned, I'm not sure of the state of these now, whether they're still being developed. The Haskell one is quite old, certainly. Bamboo is a little bit more recent, but I'm not sure if that is still being used. But we're concentrating on Solidity anyway. And then in terms of the clients, the main one that is used, the most popular one at the moment, is Geth. The Open Ethereum, which used to be called Parity, is less popular than it used to be. More popular is Nethermind, and the Nethermind project is doing a great deal of work generally, not just in terms of its the Ethereum client. It's also doing a lot of work on zero knowledge proofs and Starknet. So they're really a really interesting company to have a look at. And then Besu is part of the Hyperledger framework. Aragon, I think that's the new client for the upgrade to Ethereum. If you want to do mining on Ethereum, I don't know how feasible this is now. I mean, I did this many years ago. They tried to make it different to Bitcoin in the sense that they wanted to stop it being dominated by hardware improvements, and to do this, they use a particular version of proof of work, this called Ethash, and it uses a data set, and this data set needs to be in memory, and so because of this, it is difficult for this to be done on very small devices such as ASIC devices, and this is what I when I referred to the mix hash, this is used in this Ethash algorithm, and so they've tried to make it so that it can be done on a desktop with a some sort of GPU, some sort of graphics card, and that it should still work. I think in the last couple of years, people have tried to include to build things that so hardware that gets around the restrictions on this, but I'm not sure how successful they have been. And anyway, it's going to be replaced soon, so it's probably not worth it now anyway. State pruning. So actually, this comes back to the idea of where the state is. In fact, perhaps I should ask this as a class question now. So I posed this this question earlier on, where I said, where is the state? And if you have a variable in a contract, where is this? So I'd like you to have a think about that and decide, think about where this actually exists. If you want to put some ideas into the Q&A to see what you think, because it's important that you get this idea this idea correct. Anybody wants to volunteer an answer to this? Okay, so they're saying the state is in the smart contract. So yeah, so the smart contract has state, but in terms of if I have a variable like my score variable and I set that to be 13, where is that 13 actually held? So that 13 is represented by some bits, which are eventually on some hardware somewhere as some magnetic state, I suppose. Yeah, so someone's saying in the EVM in the nodes. So yeah, that's getting closer to it. The state tree, not exactly. In the state tree holds. So the state tree is in the block, and this holds a sort of compression of the state, and it holds we hold the root of that state tree in the block, and so as the blocks are passed around, we'll get something where we can verify the state, but the actual variable itself is not in the block. So what actually happens is that the state in a contract will exist or can exist on some nodes, and different nodes will hold different things, so they don't have to hold the state if they don't want to. But I'll talk now about some particular node. So if you want to run what is called an archive node, you can do this. And this means that this node, when you run the client software for this node, this means that it contains all of the possible data in Ethereum. And the state itself, so all of the variables in all of the contracts, these are not stored in the blocks. What happens is your node will get the transactions and it will keep track itself of the state, and it will store that state probably in a database. So if you're using the Geth client, it's in a database that it has as part of the client. and it updates that database as it receives transactions. So if you start up a node now and it needs to get the state of a particular smart contract, it can do two things. It can go to another node and ask the another node for the latest state of that contract, and then the other node can supply those details to it. Or it can, as part of its synchronization, it can actually apply all of the transactions since the start of Ethereum and update its local state until it gets to the current state. So effectively, the state of Ethereum is really only held completely in these archive nodes. So not all of the nodes on the network will hold this state. And it's certainly not held within the blocks, because the blocks really just hold a commitment to the state. They just have the Merkle roots of the state so that they can validate that the state is correct, but they don't actually hold all of that data, because it is a large amount of data. I mean, it's more than I don't know what it used to be, more than 4 terabytes. I guess it's probably a great deal more than that now. And so it's not feasible for everybody to store that. So only certain nodes will store that. In terms of, so the question, if they give the wrong state, well, you can check this. So the fact that you've got these Merkle roots means that you can check the fact that the things are valid. That's what they're for. So you're using the blocks, the block header, to check that we're in agreement about the state, and to check that the state is valid, and you can compare that to the state that you hold and verify that it is correct. But it is certainly, the state is not held within the blocks themselves, but it is made up of by applying all of the transactions from the that are contained in the blocks. When you say off-chain database, well, it's the database is created by the client, so it's sort of regarded as being on-chain, I suppose, in that sense, in the sense that it is part of the main chain. It is holding state of the main chain. Off-chain generally means other things. Yes, the synchronization of the global state is achieved by consensus. That's what the consensus is for, is to come to agreement about the state of the global state of the system. And where are these archive nodes? Well, anybody can run one of these nodes if they want to. When you start the software, the client software, you can specify what type of node it is that you want to run. So you can choose. And then certain projects will run archive nodes as well. So for example, Infura and Alchemy will run full nodes, archive nodes. If the state, well, not exactly lost if nobody ran an archive node, because it can be reproduced, because you can rebuild the state from all of the transactions. The only way that the state would be irrevocably lost would be if we lost the transactions. So you wouldn't be able to recreate the state. So this is how you should think about the values of variables in your contracts. And also this answers the question about events, is that if we want these things, if we want to know the current state, we can rebuild them by applying the transactions. And this is where, so to answer the question about events, and are they stored on the blockchain? Well, no, they're not. But what we can do is we can create the events by running the transactions. But there is a shortcut to that by using the Bloom filters, because we can query blocks to check whether an event has happened within that block. If we're looking for a particular event, we can use the Bloom filter and we can query a block and say, did this event happen within this block? And it will give us back an answer of either no or possibly. So if it tells us no, then we can just accept that, and we don't have to look any further. If it says possibly, then what we can do then is look at the Bloom filter within the transaction and say, did this event happen from this transaction? And if the answer again is possibly, then we would rerun that transaction on our locally to recreate the transaction receipt, and then that would give us the event. So that's the kind of the process you'd have to go through. So when you're thinking about state on Ethereum, think of it in that way. Think of it as being built up over time from the transactions. So it's not something that is sort of necessarily passed around as in one big chunk as such. And the blocks certainly don't hold a state, they just hold commitments to it. But if you want the state, you can build it by running the transactions. Is incentives to run an archive node. You may want that because you want to have quick access to all of the state. So there are use cases for that to do with the way that some projects work. And it's possible to explain the path from request to response for a query like get score. Okay, so get score is a view function. So if you call that from say we were calling this from a web page, what would happen is you make a call, what is called an RPC call, to a node. So you effectively make a connection to a node on the network, and you say to that node, please run this function get score, run this view function get score, and send me back the result, and the node will do that for you. Whether it's routed to an archival node, you don't really know. So it's up to the node you're interacting with to supply the answer to that and get the details that it needs for that. So that's, in terms of what you're doing, you don't need to, you just kind of assume that node will be able to get the state in some way. Is the Bloom filter the structure the graph is querying? The graph will query the Bloom filter in the sense that the graph uses events. So just for those of you who haven't come across the graph is a project that is there to provide sort of analytics about the blockchain and provide sort of enriched data about the blockchain and what is happening in a way that and a way to build relationships up between say different contracts and different users. So what it does, what the graph does is it has have people who run software that look at the events coming out of contracts, and they store the details that they get from these events in a database, and then they can enrich that data in the database so that to give a richer set of data, and then other people will query these databases that the graph provides, and they pay to do that as well. So they will look at the Bloom filter because that's a way of checking whether they need to look for an event, but then they do need to get the event itself to get the details of the event out there. So the question, a node produces a block, loads transfers mempool into the block. So if you're talking about a miner here, yes, so the miner will pick transactions from its mempool. The mempool that a node has may well be different from other mempools in the system, but just depending on which transactions they have seen at a certain time, so they're not necessarily the same as the other mempools, although they will be roughly the same. Each node would hold a different blockchain and transactions. Well, the node should have the latest block. If it's synchronized, then it will have the latest block. It may have different transactions because these transactions could have arrived since after the latest block, but the transactions that it has consensus about will be the same as the other nodes. So there will be the transactions that are in the blocks will have been seen by all of the nodes, and they have come to consensus on that. The metadata of the whole ledger is increasing. Well, the state of is increasing every day. Yes, and this is a big problem for Ethereum. And yeah, it's massive. If you want to run a node, you require some very good hardware to do that, particularly very good storage to do that. Yeah, so it is a vast amount of data that is happening all the time. Definitely. So yes, so hopefully that's cleared up this idea of where the state is. It's very important that you get that sort of clear in your minds, because it's not immediately obvious about, when you look at blockchains, it's not really obvious where things are actually stored or where we get values from. So I hope that's helped. And that was that was from a while ago. The question was about pruning. So yeah, this is the fact that when you run a node, if you don't want to hold all of the state, you can prune the state. So you can, for example, get rid of accounts that don't have a balance. You may drop those from your database, or you may have some other optimizations where you don't keep certain details in your database that are older than a certain time. That whole area is quite complex, and there are all sorts of improvements happening in that area, but they're beyond this course. So we kind of mentioned those a little bit in the advanced Solidity course, but you don't need them for this course. Yeah, so I mentioned mining, test networks. Yeah, I think you're probably aware of some of these. There's these have increased over time. The ones we tend to use Rinkeby, just because that's just historic reasons. We use that for a while, but they're all pretty much the same, although they do work slightly differently. So just to preempt a question about proof of authority, this is a different type of picking a block producer. So it's in this, you have a white list of block producers, so people who are allowed, or addresses that are allowed to produce a block, and there is just a round robin event. So you just go from one entry in this list to the next one. So they just take it in turns to produce blocks. And for test networks, that's fine. You just want to make sure that blocks are produced regularly. You're not so worried about the sort of issues of decentralization there. Okay, so that's everything I wanted to cover there. And then there's quite a, let me share the other thing. There's quite a bit on the homework side. So I'll go back here. All right. So for the next piece of homework, which you can start now, and then you have tomorrow and the weekend also to continue with. The first bit is just to make sure that you're familiar with using a wallet and using a test network. So yeah, just get some test ether from say the Rinkeby faucet. There are a number of faucets. The main one is very flaky. I don't think it's working at the moment. It really does come and go. The one I've linked to here is a little bit more reliable. It only lets you have a small amount of ether, but at least it works. So just make sure you're happy with this procedure, that you can use a wallet such as MetaMask to hold some ether and then send it to some of the people in your team, and also then look for the transactions that you did on the Block Explorer and start to dig into a little bit about the transaction. Check the details that you can see in the Block Explorer, make sure those are what you expect, and look at things like the gas. So when you use MetaMask, it will tell you how much gas it expects it to cost. So then have a look and see if that was accurate, and have a look at the way the gas is split up when you look at it on the Block Explorer. So that's the first one. The second piece of homework is to write some Solidity, and we're going to build a contract which is going to be a token, which we're going to call Volcano Coin, and this will eventually follow the ERC20 standard, although in this first piece of homework, we haven't got all the pieces there yet. Now, I know there are libraries available for you to make this process simpler. And I mean, generally, I would say use the libraries, but just for this particular exercise, don't use the libraries. I want you to do this yourself, and just to make sure that you're happy with all of the basic structures and the syntax in Solidity. So the details here go through the various steps, tell you how to set up your contract. Well, I want you to create a variable that is going to hold a total supply, and you need to be able to read that value. And we need a function as well that allows us to increase the value of our total supply. And then we also want the concept of an owner of this contract so that we can then restrict access to various functions. So this will mean using a modifier, and then we want some events changed. And then we come to the kind of the nitty-gritty of token contracts, in that we have to keep track of the balance that a user has. So we need some type of data structure to hold the balance. So you will have to decide what the best data structure is for that. And so create a variable of that type of data structure to say how many volcano coins a particular address has. We then will need to be able to read a balance for an address from the contract. So think of the ways that you can do that. We'll need a constructor so that the total supply is given to the person who owns the contract. And then we need a means of transferring tokens between users. So you'll need to write a function to do that. And I've given you the details of some items there. And then we also have to add events as well into our functions to show what is happening. And then I want you to try creating a struct, which is we're going to use as we further develop this. We're going to use this to hold more details of what is happening within our contract as well. So those are the last 2 points. It's a little bit more complex there. Okay, so that's the homework. We've got a few minutes so you can make a start on that now. I'll go through the rest of the questions anyway as well. Just answer the top one. In teams or individuals, so it's up to you, but it's probably best to do it individually, because obviously you want the practice that's writing the contracts yourself, so it makes sense to do that. But if you want to work in teams or in pairs, that's also good. That's fine. The license identifier is there to show people what license your code has. It's not run as part of the contract. It's not in the bytecode, but it's there for people who are reading the source code. So yeah, the question about the attack based on queries. So that's not, it's not, although there is no gas, you don't have to pay for them. The gas limit is applied to the query. So for example, if you call a view function that has an infinite loop in it, for example, then that would hit the gas limit, and the EVM would stop, the client itself would stop that running. So it's really up to the client software to prevent that being misused. And the clients obviously can choose to refuse connections if they think they are being abused. Yeah. So it's really done at the client level rather than the contract level there. Okay, so that's all of the questions, I think. I've put the homework into Discord, so you should all have access to that. As always, if you have questions, then please do ask them, and otherwise, we're almost finished anyway. So, but please do carry on with those homeworks, and I hope you enjoy doing it and have a good weekend also.